Hey guys, the videos are best played on 1.25 speed. Google tends to slow down my voice, and YouTube does as well. Last video we talked about a little bit about the energy chain. Started with the sun and went to the finally electricity at the very end, which I thought is a pretty cool way to think of energy. Now, energy. Okay, I will say this: energy cannot be created or destroyed. Now, the thing about energy being created or destroyed, well, now this little point brings a point of contention. Okay, a little point of contention would be like, well, wait a minute. Where did energy come from originally? So this here, the created part, is always an awesome classroom discussion. And if you want to comment in Google Classroom about that, you can with each other. But this is always a point of contention. Let's say that we're going to leave that out of this discussion and realize that you do have. Now, obviously, energy had to have come from somewhere at some point, according to the way that we live and our brains work. So, but now this statement here relates to all energy that's already here. So this is called what's called conservation of energy. Okay, this is going to be an important one to look at, because when we look at the conservation of energy, we look in terms of energy in a system has to equal energy out of a system. Okay, so let's just look in terms of your car. Okay, so let's say I take my car and I put gasoline in my car. Okay, let's see what I'm getting out of that gasoline. Well, first things first, out of a car, what I really want to get out of it is motion. So what I'm getting is motion energy, otherwise known as kinetic energy. We'll talk about that later. I'm also getting heat. Okay, the car actually heats up pretty even better than it does cause motion. So cars are definitely they're givers of heat. They also actually gives off a bit of chemical energy as well out the exhaust. So look, the amount of gas that I put in has to equal all the energy out. So the gasoline would be more of a chemical, okay, energy, and it has to equal the out. So the motion, the heat, and the chemical, if we add up all this energy, it can never be greater than this. Okay, and vice versa. This can never be greater than all this. So this kind of gives us a good example of conservation of energy. Now, we're going to take a look at it in simple terms. Okay, we're going to talk a little bit about roller coasters, and I'm pretty sure that you've all been on a roller coaster, or most of you have. And when you look at a roller coaster, in the old days, the old roller coasters they had, especially I think there was one at Rocky Point in Warwick. Your parents can appreciate this. I used to go there all the time when I was a kid. There was an old roller coaster. It was called the Cyclone. And the cool thing about the Cyclone was that it was an old wooden roller coaster. It was kind of scary because it was just a single car. And what happened was, let's say here's the first hill, okay, of the Cyclone. Like the car got brought up to the hill, the crest of the hill. So, the car got brought up to this point here, the cart. And it was brought up from way down on the ground, and it was given some sort of energy to get up to the top of the hill. And then what happened is there were no loops in it or anything. It had a nice big drop. Okay, and then, you know, a couple hills, and I won't draw the whole thing, but this is a nice picture because what I'm going to do is I'm going to label this a little bit for you. Okay, the roller coaster was brought up a height. Okay, that was brought up a height. Okay, that's the first thing that happened. The roller coaster also has something called a mass. Okay, I could take that roller coaster, stick it on a scale, find out what the mass is. And the thing is that there's also a third feature of the roller coaster. Since I brought it up a height, it's got a mass. Gravity is going to be the thing that pulls it down the hill. So this is your first introduction to something called potential energy. Okay, so potential energy. We're going to call potential energy GPE. Okay, so if you want to box that in, you can. Gravitational potential energy. So look, if I bring this roller coaster up even higher, okay, my gravitational potential energy is going to get much more because the roller coaster has an opportunity to build up more speed because I bring it higher. At this point, though, it's not moving. It's stuck on the top of the hill. This is the point where you're in the roller coaster and you're wondering when it's going to let go. So look, I lift up this mass a certain height and in the expectation that gravity is going to do something to it. Okay, this is called gravitational potential energy. And what I'm going to do is I'm going to give you the formula now to calculate gravitational potential energy. Mass times gravity times height. So the gravitational potential is mass times gravity times height. Okay, and let's work this one out very quickly. And I'll get you like a height here. We'll say this is 10 meters. We're going to call it negative 10 meters because it can fall down 10 meters. Let's give it a mass. Okay, I'm going to give this thing a mass of, we'll say 100 kilograms. Okay, and we know what G is, right? Negative 9.8. So, look what I got. I got a formula to solve for the gravitational potential energy. Mass, gravity, height. So let's do that out over here. Mass is 100. I'll leave the units out for now to leave some space. Gravity, negative 9.8. The height is negative 10 meters. And I call it negative 10 because I want to cancel these out. Okay, I want to have a positive energy value. And then when I solve for all this, 100 times 10 is 1,000 times 9.8. My answer is 9,800, well, look, kilogram meters per second squared meters. Look at these units. Kilograms, meters per second squared, meters. So in reality, it's kilogram meters squared per second squared. I don't like those units. So what I'm going to do is I'm going to change this weird little unit. We're going to call it a joule. After, yep, you guessed it, after a scientist. So we're going to call it 9,800 joules or 9,800 J. Okay? So this is how much potential energy this thing has at the very top of its path. Okay? I'm going to stop there because it's about 10 minutes. And you should be able to calculate the potential energy of something. Now look at this. I know we're going to go a little longer than a few minutes, but let's say I were to get something that it's a lot heavier or a lot more massive. Well, the gravitational potential energy gets greater. So it's almost like if I took a bowling ball and I held it above my foot. Well, if I held it above my foot at 1 meter, I dropped it, it hurt pretty bad. It might even break a bone. But if I took that bowling ball and I lowered the mass, like if I made it like a baseball, it wouldn't do any damage to my foot because it doesn't have as much energy as the bowling ball does. So again, potential energy has to do with the height, the mass, and gravity. I'll leave it there.